Hi there. Let's deal with the topic on pressure now. Let's look at this can. When we dump it into some ice, we notice that it implodes inward. And one of the reasons why this happens is pressure. And so right now, when the can's here, it's heated up on the hot plate, and that causes particles to leave, creating low pressure inside the can. And pressure always goes from high to low. So when we put the can into cold water, what happens is the high pressure wants to go in from the outside to where there's low pressure, and it implodes. Let's talk about confined fluids. We mentioned this before. We know that due to the particle theory, liquids cannot be squished any closer together. However, gases we can compress from here to here, and we can increase the pressure as a consequence. However, liquids, they're virtually incompressible and very important for hydraulics, which we'll see in the next topic. Hydraulics help with liquids. Here's another little pressure trick. So this guy smashes the cinder block, and the man's lying on the bed of nails, and yet he doesn't get hurt. And that's because we're spreading the pressure of each individual nail out over a large surface area. Liquid pressure acts in all directions, as does gas pressure. And as you climb higher in altitude, pressure decreases, and that's due to the following. Air pressure has to do with an imaginary column of air, and the weight of the air pushing down on you creates air pressure. When you go higher up in altitude or elevation, that column of air gets less and less, so the weight pushing down on you, or i.e. air pressure, gets smaller and smaller. So the higher the elevation, the lower the pressure. So high pressure down here, low pressure higher up. And again, it has to do with this imaginary column of air. However, when you go underwater and you go down deeper and deeper and deeper, the opposite happens. Now it's not a column of air, it's a column of water. And as you reach deeper and deeper depths, that column of water pushing down on you gets bigger and bigger. So water pressure depends on depth. So here, deeper down, we're going to have high pressure, and here lower up in the water we have low pressure. So what do you notice about this water tower? So here's the water, starts at the top and goes down, and you should notice here's the band, whoops, the water pressure. We have bands to help keep the wooden tower together. So these are metal bands that hold it together. And the spaces between the metal bands are larger up here because there's less pressure. But as you go deeper in here, we have higher pressures down here, which means we need more reinforcement. Same with this. So look at water spurts out of here and it only reaches about there. And then midway down the bucket, water squirts out here, and then look at how far it squirts out here. And that's due to pressure. We have high pressure coming out of the hole here, medium pressure due to the height, and low pressure here. So pressure is when a push squashes down on something. Walking pushes on the ground. If the ground is soft, it gets squashed and we leave footprints. If the ground is very soft, we leave deeper footprints, and we can make less pressure on the snow by spreading out the push or the weight with snowshoes, or even we use skis, and the skis distribute the force over a larger area. However, which shoes do you think you would push hardest on or create the most pressure when on a dance floor? Right there, probably. Depends, I guess, if we just used our heel. Maybe ice skates would be the greatest pressure because that's the smallest surface area. We use barometers to measure air pressure, and we have a formula that we should memorize, and that is P pressure is equal to the force divided by the area. The bigger the area, the lower the pressure. The stronger the force, the higher the pressure. So we could find pressure inside this piston if we knew the force was 5 newtons and the surface area of the piston was 2.5 centimeters. We plug in our numbers. Force is 5 newtons divided by the surface area, 2.5 centimeters squared, and we would get 2 newtons per centimeter squared. Consequently, pressure is usually in the following metric units: pascals. And a pascal is equal to 1 Newton per meter squared. And so this Newton per centimeter squared would not be equivalent to pascals. We'd have to convert the surface area to meters squared. See, let's see if we can calculate how much pressure this tank of water is pushing down on, let's say there was a floor here. And we know it's water, which has a density of 1 gram per 1 centimeter cubed. So to find that, step one, we'd need to find the volume of the water in the tank. So that's length times width times height. You can't kind of see it there, h, height. So let's do that. Let's take the length, which is 50 times 10 times 20. So 50 times 10 times 20 equals 10,000 centimeters squared. Step two, we want to find how much mass is that? Well, thanks to the fact that we know if we had 1 gram of water, that would be a volume of 1 centimeter cubed. 1 gram per 1 centimeter cubed, because the density of water is always equal to 1. So 1 divided by 1. Okay, we don't have 1 centimeter cubed, we have 10,000 centimeters cubed. But because this fraction has to equal 1, that's 10,000 grams of water. So that's our next step. So it has to be 10,000 grams of water. Next, we're going to convert that to a force, because remember, P, pressure, is equal to force divided by the surface area. Now, if we know what kind of pull of gravity 10,000 grams of water is pushing, then we can put that into the force. Well, on Earth, mass is related to force. 1 kilogram of mass equals 10 newtons of force, and 100 grams of mass is always equal to 1 newton of force. So we don't have 100 grams, we have 10,000 grams. So what would that be? Well, what's the difference between this and this? 100 times, so we times this by 100, and now we have our force. Next, we need the surface area, but it has to be in meters squared, not centimeters. So we need to convert these to meters. So that's 0.5 meters, and that's 2 divide by 100, that's 0.1 meters. So our surface area is 0.5 times 0.1, and that's 0.05 meters. Step 5, we now have the surface area, which we can plug in there, and we have the force, 100 newtons, that we can plug in there, and therefore we can find pressure. Pressure is 100 newtons divided by 0.05, which is 2,000 pascals, or convert to kilopascals, that's 2 kilopascals, kPa. Let's try one more example. Okay, find the pressure of this water tank. So step 1, find the volume. That's the length times width times height. So 5 times 5 times 10, 250 centimeters cubed. Now find the mass. Well, 1 gram is always equal to 1 centimeter cubed, so 250 centimeters cubed is 250 grams. Okay, once we know the mass, 100 grams is 1 newton. So if we have 250 grams, that's 2.5 newtons. So remember, pressure is force, which we now have over surface area. Don't forget, surface area cannot be in centimeters cubed. So let's convert this 0.05 meters times 0.05 meters. So that will give us in meters squared. So 0.1225, 1, 2, 3, 4, whoops, one more zero, 0.0025 meters squared. And let's double check our math here by pulling up my calculator. 0.05, 0.05 times 0.05 equals 1, 2, 3. So 2 zeros. So let's go back to the PowerPoint and let's go full screen, and it's, get my pen going, it's 0.0025. So let's find pressure. Pressure is force over surface area. So let's plug in our numbers. What's the force? 2.5 newtons. What's the area in meters squared? 0.0025. So again, let's use our calculator to find that. Clear. 2.5 divided by 0.0025 equals 1,000 pascals, or 1 kilopascal would be the pressure. And so there's my lesson on pressure.